Hello everyone, my name is Miley Yao. I am from University at Albany and today I'll be presenting our paper that I've been working on with my advisor Sherry and Reza. The title of our paper is Analyzing Student Procrastination in MOOCs, a Multivariate Hawks Approach. So let's just get started.
Let's first talk about student procrastination. It usually means a voluntary delay when it comes to learning tasks. Procrastination can be harmful, especially to students' academic performances and sometimes even to their well-beings. It is very prevalent among students, especially in massive open online courses or MOOCs, because a higher level of time management is usually required. So, due to its importance, past research has tried a couple of ways to model student procrastination, mainly using static methods, such as using self-reported data or time-related measures. However, such static methods can be inaccurate in modeling students' activities on a continuous timescale. So as a result, in this work, we want to study some important temporal factors of procrastination that haven't been heavily discussed before. Specifically, we want to answer these three research questions. In the first research question, we want to explore the possible dependencies between past activities and future ones, as opposed to methods that only consider the average number of activities during a time period as example. In the second research question, we want to model the dependencies between students' interactions with one learning material to another if there exists any. Last but not least, we want to explore the association between these time dependencies and student procrastination. To answer these questions, we want to study each student's procrastination behaviors by looking at their interactions with all learning materials in a learning module or the unit of an online course. And the method we use is multidimensional Hawks processes, which are the family of point processes that models time sequences given the arrival times of observed activities. So a natural question to ask would be, why do we even want to use Hawks? One reason is that, as we just mentioned, we want to model students' interaction with different learning materials provided by the courses. And Hawks processes, as a stochastic model, is able to model students' activities by looking at all their timestamps, which in turn can help us explain students' behavior in a temporal point of view. Another main motivation is that, unlike temporal models that only rely on the average number of activities as input, Hawks is able to model more time sequences that are more complicated. So, as an example, in MOOCs, students' activity do not usually take in a regular manner. Their learning pace may also evolve over time, and using Hawks enable us to model such irregular behaviors and can help us even differentiate the differences of behaviors from two students, even if they had the same total amount of activities. Now we can formally introduce our method, that is, given the history of one student's interactions with one learning module, or we call it a student module pair, we model all its activities that correspond to all learning materials as multidimensional Hawks processes. Specifically, we consider three types of learning materials in this work, which are assignments, lecture videos, and discussions, where each of them is called a dimension in Hawks processes, and all of them are modeled simultaneously in order to capture three important time dependencies. But let's first look at an example to see what these time dependencies are. As example, suppose we observe a student's activity as described here, where each activity is represented by its arrival time and its learning material type. So on this figure, it is represented as a vertical line on the timeline in its corresponding dimension. Then we can see that some of the activities are considered as the result of external stimulation like deadline, and some of them are triggered internally by the previous activities of either the same learning type or of other learning types. So to summarize, the first thing that our model is trying to capture is the triggering effects of external stimuli to each of the three learning materials. However, when it comes to internal triggering effects, the model also tries to capture the within dimension dependencies that we refer to it as self-excitation, as well as the between dimension time dependencies, which we refer to it as mutual excitation. So formally, each Hawkes process on each dimension D, where D can be either assignments or discussions or lecture videos, can be characterized by this intensity function that models the number of activities on a continuous time scale. This intensity function has a very intuitive structure, which is very similar to the example we gave in the previous slide. Particularly, the intensity function consists of two components. The first one is mu_d that models the activities that are triggered externally, or we call it base rate here. And the second component here is the expected number of activities happened or take place in dimension D and that are triggered by D prime. So alpha D prime here describes the excitation rate of dimension D that are triggered by dimension D prime. And finally, we use this beta to model the decay rate, which describes how fast the effects of past will decay over time. The dataset we used in this work is from Canvas, which is an online platform that provides different online courses where different learning materials are provided, such as assignments, discussions, and lecture videos. We picked a computer science course for its large amount of historical data. Specifically, we used its log files to extract students' historical activities that includes all of their learning material types and their Unix timestamps. So in total, we ended up having 731 students plus their around 946,000 learning activities. Our experiments are conducted mainly to answer the three research questions. Specifically, we explored these four following aspects: the goodness of fit, model parameters analysis, their association with student procrastination, and finally, their association with student grades. And we're going to look at them one by one. In this part of the experiment, we want to explore research question 1, which is if future activities actually depend on the past ones, or a memoryless model such as Poisson process would be good enough. So what we did here is to fit all the observed timestamps into multi-dimensional Hawkes model and a single-dimensional Hawkes model, meaning that no between-dimension dependencies are considered, as well as a Poisson process model. We computed the RMSE of the estimated intensity using 3 different models, and as we can see in the table, multidimensional Hawkes model achieved the best fitting performance, meaning that such dependencies do exist and can be used to help improve the prediction. We can also see from this figure of the intensity of a sample student module pair that activities do not come in a regular pace in any of the learning material dimension. The second experiment we did is to have a correlation analysis on the estimated Hawkes parameters in order to answer research question 2. Namely, if a student's interactions with one learning material depends on another. So in this correlation matrix, we can see that the self-excitement parameters alpha DDs are all negatively correlated with base rate and decay coefficients, meaning that higher briskness usually comes with less influence from the deadlines. However, the past may affect future for a longer period of time. So example would be that a student divides a big task into only a few smaller tasks, so that They return to the smaller tasks less often, but in average, more bursty activities within each smaller task are going to happen. So another observation is that the influence of lectures and discussions to other types of learning materials are usually more consistent, as we see the high correlations between all the excitation rate alphas. On the other hand, however, fewer discussions and lecture activities may happen as the result of assignments activity, since the excitement in these dimensions are not very highly correlated with the dimension in assignment.
The third experiment was conducted to answer research question 3.
Particularly in research question 3, we want to explore the relationship of procrastination to students' behaviors that are characterized by the Hawkes model. So we started this experiment with clustering students by the self-excitement parameters that are averaged on their dimensions, namely the average alpha in dimension assignment, in dimension lecture, and in dimension discussion, respectively. We used k-means and realized that a cluster of 2 have the smallest SSE, and we see that in each cluster, different behaviors are observed. So, for example, type 1 might have divided big tasks into many subtasks, which leads to more frequent but less dense activities throughout the learning processes. On the other hand, type 2 tends to intensively interact with one learning material for a shorter period of time, which possibly followed by a very long pause, which explains a high excitation but low base rate. We then check any possible differences between the two clusters in terms of student procrastination. Specifically, we use this normalized delay as the proxy of procrastination in each learning material dimension. As we can see, in the less frequent but more bursty group, which is type 1, the delay in each dimension is much lower comparing to type 2. So to summarize, non-delay group has less frequent but more bursty behaviors, whereas more frequent but less bursty behaviors are observed in the delay group. Finally, we want to use experiment 4 to see if Hawkes parameters can capture something more than just the normalized delays.
Specifically, we propose a new delay measure based on the normalized delay. We add a second term here that quantifies the potential delay in other dimensions by delaying the activity in dimension D, and our results show that the new delay measure has higher correlations to students' grades comparing to just the normalized delay measure. In conclusion, we propose to use multidimensional Hawkes processes to model procrastination. We showcase that multidimensional Hawkes processes have a better fit to student activity counts in comparison with their single-dimensional version and the Poisson processes. Our experiments also review 2 types of behaviors in the data that are associated with different delays. Specifically, in delay group, we observe higher within and between dimension excitement, but lower base rate. However, in non-delay group, we saw higher base rate but a lower excitation in all dimensions. We also showed that between dimension dependencies in the multidimensional Hawkes model can better explain students' grades. We made our implementation available here, so please feel free to check it out if you're interested in our work. And that is all for today's presentation. Thank you so much for your time and your interest. Please let me know if you have any questions.